That weird sense of déjà vu you're gonna feel on this one is entirely normal. It's expected, not exactly intended though. But it's fine, everything is okay, there's no glitch in the matrix. We're just gonna pretend last week never happened. So, what exactly did we do in the quote-unquote last episode? We had a look at this made-up fictional CPU, virtual computer, that's reduced to some very fundamental basics of how most modern computers operate. And today we're gonna have a look at how we actually write programs that can be executed in a machine like this. Let's have a quick recap by loading in the very first program we looked at last time. Remember, we have the memory, the central thing around which everything revolves. And in here we have a couple of different numbers in individual memory cells, which are just numbers for now. And our computer operates in a 4-step cycle. Actually, let me notice on the VOD from last time, you didn't see the last step, so I'm quickly removing the current music, background music title indicator. We read the operation at our program counter, our bookmark. We interpret that as an operation. This time it's write accumulator. Write accumulator requires an address. We need more data than is provided in a single memory cell, so we load the next memory cell over. We read the argument, which gives us a 6. So write accumulator will write a value from memory address 6, so over here, to the accumulator. That's happening in the 3rd step when we process the operation. So now the accumulator, the 2nd register below the program counter, now has a value in it. And lastly, we increment the program counter so we can operate with the next instruction. The first 2 memory cells were used already. We're jumping to memory cell 2, or address 2. And we begin the cycle anew. We read the operation. This one is add, for addition, which also needs an additional value for the address. 7. When we process the operation, we're going to add the value in address 7 to the value in the accumulator. And then we jump forward to the next instruction, which is read accumulator. We read the address it needs, address 8, and we write the current value of the accumulator into address 8, increment the program counter, and this is where we last time explained that the computer has no idea what the numbers mean, whether they be operation or value or completely random bullshit. 85 is not an instruction, so this computer will kind of go on strike. Very simple process, very simple program, in fact just 3 instructions. We combine 2 values from memory and the sum goes into a 3rd. It's one of the simplest computer programs you can write on this specific machine. It involves 9 different memory addresses though, and a bunch of numbers that by just looking at them you wouldn't quite understand. Without having a table next to you that explains all the different opcodes that would tell you that 2 is write accumulator, you wouldn't be able to decipher this at all. And even if you had that table, you might still get lost in this. This is just a list of numbers. If I just pick a random number, like this one here, I can't tell, is this an operation? Is this a value? Is this an address? What is this one? I can't tell, because there is no way to tell. randomly. You have to go through the entire process of running your program. And the funny thing being that this one could be a value and an operation and an address and something completely different. It could be everything. Because there's no fixed logic for every memory cell. It's all just a matter of what is the computer doing with those numbers? What are you telling the computer to do, in a way? The basic computer is pretty dumb. All the intelligence, all the actual logic is purely in the hand of the programmer that feeds the computer this code. The computer is just computing, it's just calculating. Very simple things. All the logic is purely in the arrangement of numbers. And since that's our job, we better understand how these numbers get arranged. So how do we do that? Well, for starters, let's talk about how we actually write this program to the computer. Because that's interesting in of itself, though let's not make this a history lesson. But just keep in mind, this is a memory in a computer. This is maybe just some electronic circuits that temporarily can hold a value as long as the computer is powered on. This could be some more permanent storage system, like magnetic storage, or flash drives, like electrochemical storage systems. There are a lot of ways. There are a lot of fun memory systems in the past, a lot of them kind of forgotten for reasons, but still. Never mind. Point being, different memories can be accessed and changed in different ways. Let's assume this is a purely volatile computer memory, as in it's not permanent storage. It's only holding the data for a short time, or maybe just as long as the computer is powered on, like your RAM. Well, we're gonna power on the computer and then have to feed in these numbers, including the information where the numbers go, which could be done either by always giving the computer a combination of a value and the address it's supposed to go in, or we just assume it's gonna start writing at some point and we just give the numbers in sequence. Different computers in the past, like way back, would actually work that way. You have a bunch of switches, physical switches, and you would input a number and then press a button, and then it would, based on those switches, just a binary value, would write a value in that specific address with a specific value. Like for this, you would have 8 switches for the value and another 8 switches for the address, and then press a button and it's gonna write that in there. Very simple, but not the best interface, especially since you have to do that for every single instruction. That's gonna take a while. Punch cards were a thing, and punch tapes, where you didn't have to do switches all the time. When you want to run the program, you could just type them in on a special keyboard of sorts, and it would punch very precise holes into paper or cardboard, whatever you had, and then later a machine could then read that in based on where those holes were. You had electrical switches or maybe even optical switches that would then read that as ones and zeros, and based on that figure out the value and address for where you write the memory, with what value. Pretty cool stuff, actually. I mean, it's a nightmare to work with for actual programs, but the concept is really cool. It's just a fun thing to... It's stuff I enjoy. I like that kind of thing. Anyway, let's assume we have a situation like that going on. We have a very primitive interface that lets us, through some means, write data into the memory, but we don't want to do that too often because it still requires some effort. In the simplest case, I would just prepare then a list of numbers like these, and they would get fed into the computer before I run it using just punch tape. Right? Not as common today, but maybe something that would happen back then. Or maybe a series of punch cards. This one doesn't need to be tape. So to write a computer program, I would have to prepare these numbers in some paper cards. How do I get to these numbers, though? Well, in my mind, I would have access to the total list of instructions my computer that I want to program for can run. All the operations it has, with the including table for which code, which number represents which operation. And then I would start to play around with a bit. I would think, okay, maybe I need to load the data, so I'm gonna need I'm gonna add two numbers. So I need to access the accumulator. For that I have the write and read accumulator. And of course the different arithmetic functions like add that change the accumulator. So I'm thinking I need to add. So there's an operation add. Okay, I can add one of these numbers with whatever is in the accumulator. So I need another instruction to load something into the accumulator so I can add to it. So I already know I'm gonna need a write to accumulator and I'm gonna need the add. And since I don't want that value in the accumulator, but somewhere in memory, I'm also gonna need then an operation to get that value from the accumulator back into memory. And that's where my write accumulator comes in. And finally, I want some values to add, and those are just written in the end. And now on the second step, I have to think about where these different addresses are. I have the specific operations, sure, but in the computer, everything is arranged by a specific address, by a specific memory cell. So I have to keep track of that. I have to figure out, I have my instruction for write to accumulator, which takes 2 spaces, 2 cells, and then my add instruction, which takes another 2, and my read accumulator, which takes another 2. And then I have my actual values plus the output, which I'm just going to write a 0 in here so I keep track of it, that it exists, but I don't really worry about what value is in there. I'm going to overwrite it anyway. And once I have this knowledge, 2, 2, 2, and then these 3, I can figure out, okay, this is going to go in memory cell 0, so this must be 1, 2, 3, 4, 5, 6. Memory cell 6 is where I'm going to read my first value. So that's the address I'm going to write into this memory cell right after my operation. And same for the add, I'm going to write the 7 for the second value. And for the output I use then 8. And I write that right after my read from accumulator. And then I'm going to write the different values I want. And then I prepare all that on some paper, feed it into the machine and run the program. And hope that nothing breaks. So while the computer gets this list of numbers, what I have is actually basically some notes scribbled down. I would just start with roughly the outline of my computer program. I want these specific operations and then arrange these operations in a sequence so I can work out the different addresses they would get written to in the computer. And then I have the exact numbers I can use for addresses to write and read data from and jump to for other things as well. That means instead of just having a list of numbers, what I actually want is writing down, for example, this is write to accumulator, and this was add, and this was read accumulator. What I as the programmer think about and what I use for my notes to write down is these operation names. I don't think about 2 and 4 and 1. That's the computer. The computer thinks about that, but I as the programmer think about write accumulator. And because I'm lazy, I'm not going to write that out as the full name, I'm just going to use a shortcut, which not so coincidentally is the same 3-letter combination you always see on the right here. Programmers are always lazy, get used to that, so 3-letter combos are traditional and very convenient. You can express a lot with just 3 letters. It's kind of weird how well that works sometimes. Or maybe I'm just used to it. Or both. In any case, I would use these names instead of the values to get a better idea of what I'm writing. Plus, I would somehow need to keep track of where my values are, right? So right now, there are just some empty numbers in here, at the bottom. I should probably keep track of what these mean, because over here I have numbers, but they follow different operations. So I know already these are one instruction. Operation and an address. Operation, address. Operation, address. Makes sense. These numbers, were they supposed to be operations? Probably not. I don't see any text in here, but maybe that was just a mistake. Maybe I just forgot to replace it. Let's say this wasn't an 85, but just an 8. So that's a valid operation in this computer, but it's not supposed to be an operation. So rather than write that out as just 8, 8, 170, 0, I'm gonna add a little new line in here. Separate this block of numbers from this block of instructions. Just a visual indicator helping me to understand that this is separate. And then maybe I also add a little note next to it. Maybe something like input A. Or just A. And this could be B, and this is sum. Oh, A plus B, maybe to make that a bit more clear. Well, that looks a bit weird now. I have these combinations of digits and letters over here. I have letters here for my operations and digits for addresses, and now I have these combinations of both. That might look a bit weird when looking at it the first time. Like, was it a typo? Especially here, that's 3 characters. Was that supposed to be something else? Well, let's add a special character, special symbol that we don't use so far, that will help us identify this as, oh, no, this is just a note. This is not supposed to be part of the actual program. This is just for me. Could also do it in here. Values. Let's keep that as is. So now I have this block of instructions. I can immediately see those are the instructions I'm running. Write, add, read. And down here I have a block of values, which have specific names. And actually, while I'm doing that, why not add those same up here as a reference? This address is supposed to be targeting A down here. And the 7 is targeting B. And finally, we write to A plus B. So without having to work out the specific addresses, I can look at this code now and work out what it's supposed to do. Assuming, of course, the program was written correctly. We always assume it's written correctly, there are no mistakes. In that case, we can just see what it's doing by reading these different notes, which is rather convenient. What is not so convenient is actually writing the program now. We made it easy to read, which is good for other programmers, I guess. If I just give them the rundown, hey, this sequence of numbers is this program. That's great. I understand what the program does, but let's assume I want to change it. Let's say I want to modify something in here. Maybe I just want to add a second add. By the way, this thing will just continue on the right, but there's not enough space here, so. Maybe let's just put this block over here. Might be nice anyway. So. Now we have a second addition. We basically make a combination of A plus B plus B, so A plus 2B. That's what we're calculating now. But because I changed the number of instructions, the number of memory cells we use for this first block, the addresses for the values will be further to the right in memory. Basically, addresses 4 and 5 are gonna have another 4 and 7 stored on there. And what's previously 4 and 5 will now be at 6 and 7. But just load the program in real quick. This is the end result. This is what we are currently having in there. This is the original program. Since I managed to move the instructions over, I need to fix all the places where I reference one of the addresses after my addition here. Everything that's below this add, or basically everything that's below this add, has to be updated to match the new references. But everything that's up there has to be updated as well, because I moved this block of values that get referenced. Everything has to be updated. But to what? I have suddenly some empty space down here, and these extra lines with comments, so I can't just count the lines anymore. That's a bit problematic. To work up the actual address, I have to now go ahead and ignore all this white space and these comments in here and just pretend they don't exist. And then I get back to every line represents one memory cell, and I can just count the number of lines to figure out which address that specific line would be. And then I would figure out, well, I could have made that easier because I added 2 instructions in here. Everything was moved by 2, so this is actually just 8. This would be 9. This would be 9 as well. Same instruction, and this would be 10. And then I would have my program working again. That's a bit of work though. Imagine every time you change something, let's say I'm changing this back now. I don't want to have 2B after all, that was just a mistake on my part. Well, I'm gonna have to adjust these all back to the original. To go back to there and that and that. And maybe I have, sometimes I change something else. Maybe I add another number in here, C, which I'm not going to use for now, but I'm just adding it. Well, now all the references for A can stay the same, but everything that's for B, or the output, A plus B, has to be updated. So this can stay, but these two would have to be moved by 1. And that has to happen for every single change. Lots of work. So not only is loading the program a bit of effort, because you have to somehow get what you've written as nodes into memory in the actual computer, you would have to constantly go through your entire program and update everything for every single edition, no matter how small it is. It can completely wreck your entire program because the addresses change. I mean, you also have to keep in mind that what we have here are operations, which the computer doesn't understand. It needs numbers. So you will also have to look up which number represents these operations and feed those into the computer rather than this text. But that's the lesser of two evils right now. It's not as big of an issue as rewriting my entire program, which might be hundreds or thousands of lines of code. I mean, realistically, we're talking about a couple of million sometimes, or even more. For a small computer like here, a couple of dozen lines, maybe a few hundred. I mean, our memory is limited to 255 cells, so at most you can have 255 operations. So, it's work, and we don't want to do work. As established earlier, we're programmers, we're lazy. Good thing we have access to a fancy tool called computer, which can do things for us. Like working out the address a specific line should be. So if we just take this program, for example, have this program now with the C added here, this program would work. There's no error in there. And it's not even that it's logically doing something completely wrong. It's still taking two numbers and adding them. We moved in this C. Let's go back up here, This was the original program, and this is what we do now. So this is the address we previously stored B in, and this is the address we previously stored the sum of A and B in. So what this program will do, if I don't change it, it will take this value and add them together, writing them in here. So it will not add 8 and 170 to write into down here, to this memory cell. It will take 8 and 5. And it will write 13, overwriting the 170. It's still adding two numbers and writing them to memory. It's not even that different from our program before, but it's still technically doing the wrong thing. It's using the wrong values and writing in the wrong addresses. The computer wouldn't know that. I could give this program to someone else and they might see that these comments talk about A and B, but the address doesn't quite match anymore. And they would see that, okay, probably an error. I might have to ask the original programmer if they meant C here instead of B, and down here B instead, or if they didn't update the addresses. A computer, completely automated system, something that has just strict functions for you see A, do B, done. It wouldn't get that. So we have to help a bit. We have to help the computer figure out what this program is supposed to be, and in the process make our life even a bit easier. I mentioned that a human programmer could see these comments and based on that figure out that something isn't quite right. And probably assume that since we're talking about AB and AB, well, we probably meant these addresses, which makes a lot of sense. So why bother with adding these numbers in here? If someone else is trying to interpret what we write, why give them specifics? Just get rid of the numbers here. And now someone can only rely on these comments to figure out which address we mean. There's no question of which one is it, the number we used or the comment we referenced. The only issue here is that these comments kind of conflict with what we want to accomplish. Since a comment would mean this is just a note, you can ignore that as far as the program is concerned. And when you write that program, you just have to delete them. But that would mean we would have write to accumulator without an address. So the rules here don't quite fit. So instead of using this symbol, this / to mark it as uncomment, let's use a different symbol to make sure someone understands we are talking about a specific address, which we haven't figured out yet. Like so. Similar to the note, this is not the actual code we put into memory. This is just a reference for someone to read and figure out, oh, we are writing to accumulator from a specific address, and we mark that address with an A. Let's look for the address with A, it's down here. This is the value we mean in here. And this is talking about B, so it must be this one. Wherever we wrote this 170, that's the address we want to use for this add. And same with A plus B down here. And this is something a computer could evaluate as well. There's no speculation, it's very clear. You see this symbol, look for the line that has this A. Ah, that's another issue now though. Because maybe I just have made some comments with A. Which line do I mean now? The first one I find? The first one with a value? Like, what if I just accidentally made a comment somewhere? Like, these are just notes. They're not part of the program. So, to make sure there's no mistake in interpreting which line is meant with A, we use a third special symbol. We also skip the space, and we just use a colon for us right now. And this marks this line as the one called A. This is not a note anymore. This is not a comment. This is now part of our program. This is important. That's what the colon indicates. And specifically, this colon marks this specific value, this specific memory cell, as having a name A. And now when we reference an address, specific memory cell, we look up which memory cell is called A. It's this one down here. So whichever cell we put this 8 in, that's the address we mean when we talk about A. And we do the same here for C. We do that for B. And we do that for A plus B. This way, I as a human can read what's going on. I'm doing operation, I write accumulator from A, I add the value from B, and I write the result to A plus B. And down here I have a couple of values. I have A, cool, that's the one I mean here. C, I don't know why it exists, but it's here, doesn't bother me. Here's B, cool, that's the second value we needed, and here's where we write the output, A plus B. So everything is pretty clear, and everything has very strict rules based on special symbols that identify different meanings. So a computer can use very simple logic to slowly work out what this would mean. So we don't have to do that ourselves anymore. So it's still a bit cluttered. It's taking up so much space in here. It's taking so much time to slowly go downwards and read everything. So my last act of laziness, I'm gonna bunch all of this together a bit. I'm gonna combine these lines since they're just one instruction. So one instruction is going to be on one line. Doesn't matter if it's just a single memory cell or two memory cells it requires. This is one instruction. And for these values, I'm going to leave them on different lines, because they are also standalone by themselves. Now to reverse this, I would just start by removing all the empty lines and the comments. So every line has something relevant for the actual program. Then we would spread out instructions which involve two memory cells into two lines. So now every line corresponds to one specific memory cell. It's a one-to-one relation. Line 1 is memory cell 0. Line 5 is memory cell 4. It's all pretty direct, very simple to work out. Which also means we can now resolve the addresses. If I look for A, I'm just going through the entire code, look for :A, and there we have it. That's the memory cell I want. That's a 6. Oh, wait. That's a 6. And memory cell B, this one down here. That's an 8. And A plus B is in address 9. And now that that's taken care of, we can remove these names as well. Don't need them anymore. And finally, to clean everything up, we can convert these operations back into their respective numbers. And now we have just a list of numbers again, which we can execute as code. Well, now this fun part begins. 8 was a jump instruction, so it's of course now trying to execute our code as our input values as code, which is not quite what we want. But no problem, if we go back to our original code, the one we actually used, we can do something interesting here. We could make a jump instruction directly ourselves to just jump past this block of values, just to figure out which address that is. And well, this is where having a knob is quite useful. We use a knob operation just as a placeholder to mark down a specific address we want to use. Since we don't have anything to attach a label to that gives this column a name, we just insert a knob here. We could just leave it at this, actually. The computer would just treat it as, okay, we don't change the value, it's just a 0. And the 0 is also just a knob. But writing out a knob in this case makes it clear this is not supposed to contain anything. Knob is an operation that doesn't do anything, it's safe to use, and this is just some kind of, think of it as an anchor point. So this jump instruction has something to log onto. And all of this, when put into numbers, would look like that. So when we now operate through our program, 3 instructions and done, and finally our jump instruction would bring us into the knob zone, which is the rest of the memory. And of course I can just delete this line and load the program again, and all the addresses are automatically correct because I didn't specify exact coordinates. I just gave the computer instructions for how to work these out, and it did so. Actually, I can also just write stuff in front. So the program doesn't start, or the actual program doesn't start in address 0 anymore, it starts in address 6. Actually, let's make a jump instruction here. that brings us to the start of the program. We can do like that. Load the program. And then we jump from the start to our program somewhere in here in memory. And it all just works. What we have in here you see down here, this is what we call assembly. Assembly isn't a very specific language, it's more the style. They all look pretty similar, but they can differ slightly depending on, okay, a bit more than slightly, they can differ depending on what hardware you use, depending on the computer. Assembly doesn't look always the same, but you can recognize it. It's always boiling down to, we have specific operations we just write in by name, and you add maybe some additional info you need for that operation. In this computer, it's only one additional value at most, if the operation requires additional value. There's additional syntax you might have to make your life a bit more comfortable, a bit easier to write program code. But in the end, it's always this very close to the actual way the computer works, but readable for a human format. These numbers up here, they're hard to figure out. Just a list of numbers, this would be a nightmare to program codes in. To write something in, to cause an actual computation to happen in the way you want, this takes a lot of effort. This requires some thinking, sure, but you can do it no problem. And more importantly, you can later look at it and figure out what the program was supposed to be. You can debug it, you can figure out where things might have gone wrong. You can easily edit it without breaking everything automatically. You can still break it though. Just a lot of things are a lot easier if you don't have to worry about specific memory addresses anymore. That alone is most of this stuff in here. Having references instead of specific addresses, and having the names for operations instead of the numbers, that's most of the work. Having comments and being able to just sort the code a bit. Maybe I should break this up as well. That's gold. That's all I need. Actually, yeah, that's fine. This up here, just the sequence of numbers. This is what we would call machine code. Machine code is the code the machine sees, the actual program the machine would execute, the exact data as it is written in memory. Assembly is a slight step above. It's still the same code, it just looks slightly different, and it has some abstraction in the form of, at least for us, these references instead of hard-coded values. Plus, of course, the abstraction of we don't give specific operation codes or codes. We just give the name for an operation we want. And while this is all pretty easily directly convertible into machine code, this level of abstraction already allows us to compile this program, or at least interpret this program, convert this program for different hardware. Let's say I have a different machine, a newer machine, maybe, which has some additional instructions, some additional operations, and the opcodes are all changed. It might still have the same operations we have here, it still has the same fundamental memory structure. We have one memory, 3 registers. We still have the operations like these that can be used just the same, but they have different codes. If I adjust my list of numbers, I would now need to go through this entire list and figure out which addresses prefer to an operation and then change the number to whatever the new computer would need. With this, I don't have to worry about that. I just give this code to someone else, and they can work out what their computer needs as an operation, as an opcode. Plus, the example I had earlier with a couple of knobs in front, that's not really uncommon. I've mentioned it last time. Your computer is essentially running a program that, while it's running, is loading another program into memory and then executes that, your operating system. And so when you run a program like a browser, the operating system will place this program somewhere in memory, but the actual address isn't fixed. Could be anywhere, wherever it has just free space. Keep in mind there are other programs running, so you can always be sure which actual memory cell you're getting. Of course, there are some abstraction layers again here where you have virtual memory, and as far as your program is concerned, it will start at memory cell 0 and whatnot, or, well, roughly. But the actual memory cell on the computer will always be different. So it's important that you can write program code without being dependent on very specific hardware addresses. Again, realistically, you don't get that anyway, but semantics. So a little bit of abstraction here helps us make the code easier to read. It hides some of the complexities of the actual machine. A benefit for us squishy humans with our squishy, fallible human brains. We don't have the certainty of silicon. Certainty? Certainty of silicon. Well, actually, silicon is not all that certain. Never mind that. We can read this, we can understand the logic, and we can even figure out how this computer is going to operate this. So we are still close enough to the hardware to figure out optimized strategies to make the best, the most efficient program for this specific computer. But we can port it to another computer that has slightly different rules without rewriting everything from scratch. Two benefits by just having a bit of abstraction. This is usually the lowest level of programming you will work with. I don't think anyone is actually working with machine code, except for some specialized fields. The lowest you will most likely ever get is assembly code, which can be legitimate, like if you're a C programmer, or maybe C++, I'm not sure if you, maybe sometimes too. I only ever really had that in C, where, okay, at some point you want to have something very specific, do some weird optimization, or do something very, very specific and very specific circumstances. You can include assembly code in C directly. So you might actually do some assembly coding, or you just do it for fun. I mean, you can fully write your program in assembly. Like, you don't have to rely on any programming language. You can just figure out what is the specific assembly you would need for your computer. Like, what instruction set are you using? And then write code for it. You could do that. No problem. You could even do full bare metal and run your code directly on the computer, not in an operating system. Anything else, you just write directly for the computer. I don't know why you would want to do that, except for maybe learning purposes. But outside of microcontrollers, I don't see you doing anything much with assembly. But it's good for you to know this. Knowing that it exists and having an idea of how everything works in hardware. And I'm stalling right now because I'm thinking if I'm only in 50 minutes and I'm out of stuff to talk about. There's stuff I want to talk about, but I was saving that for the next time. And I don't want to forget something important again. This went way too smoothly. I forgot something. I bet I forgot something. With assembly, we convert assembly back to machine code. We have that. Advantage of assembly. No, I don't have any more than this. Well, maybe we can spend a few minutes and talk about the features of this specific computer, just as a reference. And for that, let's actually switch the view slightly. Let's go to this. Right, so let's go through the different operations we have. First, we have the no operation, which is not doing anything except we go to the next operation. Then, one you already know, read from accumulator, write some memory address to the accumulator. We have write to accumulator. Sorry, I got those mixed up. The read from accumulator was, of course, writing to memory cell from accumulator. Write to accumulator is writing from a memory cell to accumulator. Then we got an interesting one. Swap. Swap is an operation that... Actually, let's maybe write a little program that demonstrates that. Write to accumulator. Yeah, just go for that. Write to accumulator. Little program. So we write to accumulator. No, that's actually not a good idea. Let's write to accumulator 3, and 3 will get 10. Right, let's load that program. So write to accumulator. We're gonna write a 10 into the accumulator. This is important now. We are right now in... Now let's move forward to the swap operation. Has no argument. One of the first ones you see that doesn't have any arguments, it's just on its own. Here comes the fun bit. Our program counter right now is 2. We had address 2. And the accumulator contains a value of 10. Keep that in mind. Program counter 2, accumulator is 10. See that happening? That's what swap is doing. Swap is swapping the values of the program counter and the accumulator. So it's working a bit like a jump. Imagine that this is a jump instruction that's just using the value 10 to jump forward. But the important bit is that it used the value that was in the accumulator. It didn't read a value from memory to figure out the jump. But more importantly, the accumulator now contains the value that was previously in our program counter. So I jump forward to this address 10, but by reading the accumulator, I can now work out from where I came with the jump. I know I came originally from address 2. So I could add a jump later. I could just store this value in memory and then make a regular jump back to this address, to address 2, or maybe to address 3 to continue from there. You might not see the value in this. I hope to demonstrate that in the next episode, but this is a very, very important operation. Swap is very important, very useful. Knowing from where you made a jump is incredibly useful. Let's go to the next one. You know this one already. It's the addition. It just takes a value from memory and adds it to the accumulator. You already have seen this other one as well. Subtraction. Subtract. We take a memory cell and subtract that value from the accumulator. Bit shift left. Probably best if we demonstrate that again. Let's see. Right accumulator. Just another value. Let's load that program. Okay, we write a value to accumulator. That's 1. And now let's do a bit shift left. Right now the accumulator is containing a 1. And then we do a bit shift, which doesn't take any other arguments. And bit shift left means we take the binary representation of the number 1 and we shift all the digits 1 to the left. So instead of 0, 0, 0, 0, 0, 0, 0, 1, we now have 0, 0, 0, 0, 0, 0, 1, 0. Or in decimals, 2. And we do another bit shift left, taking all the digits, moving 1 to the left, and the most right one is just filled with a 0. So we get 4. Bit shift is working in binary, so every shift is multiplying, or bit shift to the left at least, is multiplying by the base of the system. Bit shift is working in binary, so base is 2, so everything shifting to the left means multiplying by 2. Same as by bit shift in decimal would be just moving all the digits 1 to the left and adding a 0 in the end. So a 1 would get to a 10, which would then be 100. In binary, that's 1, 2, and 4 equivalent. And there's a specialty about the bit shift. Let's change the value we have in there. Let's say 128. Let's do that. No program. Alright, so 128. If we bit shift this, multiplied by 2, we're essentially getting an overflow. The same thing we talked about last time with, or actually before last time, the adding 1 to the highest value or deducting from the lower values. We have a number circle. We always go back to the highest value or to the lowest value once we reach the limit of what we can represent in a single memory cell. Happens with a bit shift 2. I'm multiplying by 2. 2 times 128 is 256. The highest value is 255. So this is going above what we can store. A different way you can think about it though, which might be simpler, with a bit shift we shift everything to the left. 128 is 1, 0, 0, 0, 0, 0, 0, 0. A 1 followed by 7 zeros. And we only have 8 digits of space. So moving this 1 to the left means the 1 is now pushed out of the cell. And everything is just filled with the zeros. And you can see the ALU flag is set. The same flag we see for over and underflow. So we know the bit we just shifted out was a 1. And the next shift is just shifting 0, so nothing really changes, except the flag gets reset because we don't shift out a 1. Now let's go one operation further. Same program, just slightly different operation, 7. It is the opposite now. This is bit shift right. It's using all the digits and moving it to the right and filling the leftmost with a 0, which is the equivalent of dividing by 2. So 64 and then 32. And this 2 has interaction with the flag. If we have just zeros followed by a single one in the rightmost place, and we now bit shift to the right, that means we move this 1 out of the memory cell, drop it, and just polish with zeros, so we set the flag again. Though this time it's not because of an underflow. We divided 1 by 2, which is 0.5, but our computer doesn't do 0.5, just 1 or 0. So it's not quite underflow, it just means the bit we just dropped was a 1. And next bit shift right is just shifting everything to the right with everything being 0, and adds another 0, so nothing changes and the flag just gets reset. Next operation, you already know this one. It's the jump operation, the standard jump operation, which always jumps forward or backwards to the provided address. And then we have jump of 0, also one you have already seen. I think we talked about that. Yeah, I'm sure we talked about that in the first one, right? Can't quite remember, it's been 2 weeks. We should have talked about that. Jump of 0, a jump operation that only jumps if and only if the program counter or the accumulator is currently 0. And if it's anything other than 0, we ignore the operation basically, or the entire instructions to be specific. Now there's a variation of this, jump of 0, and it's jump a flag. Same logic, it's a conditional jump, but this one doesn't trigger if the accumulator is 0. It triggers if this flag in the LU is set. So the same flag that we trigger or that is getting set when we have an over or underflow, or as we saw earlier, when we move a set bit, a 1 out of the memory cell with a bit shift, left or right, doesn't matter. That flag can determine if this jump a flag, opcode 10, reacts and does a jump or is ignored. That's how we can react to this flag being set. We use this jump a flag. If this flag was set, it will cause a jump, and we can do special code to deal with the case where we had an overflow, for example. And if the flag was not set, then we know everything was fine. Read from I/O, opcode 11. You know that one? We take the value that's in the I/O register and write that to memory. And write to I/O, take a value from memory and write it to the I/O register. And opcode 13 doesn't exist anymore. We have 13 different operations. We have the NOP operation, opcode 0, and then 12 actual operations that do something, potentially. And that's all the computer can do. And with that, you've seen all the opcodes, in case you were curious. That filled at least 50 minutes. And with that, I'm gonna end it for today. It was a shorter one. Next time is probably gonna be a bit shorter as well. I don't want to cram everything into one stream. I don't think I can properly keep track of everything. Keep track of the structure. And hopefully by the end of the next stream I'm gonna have a little surprise ready for you. We'll see how that turns out. And until then, have a lovely Sunday. Bye bye.